Good morning, one and all. My name is V. Abhijit Kumar. My roll number is 24951A6602. I'm studying in third semester, Computer Science and Engineering with the specification of Artificial Intelligence and Machine Learning, Institute of Aeronautical Engineering. In this presentation video of the complex engineering problem in the subject of probability and statistics, I'm going to explain about the topic of queue delay prediction using MM1 and MG1 models in industrial logistics. First of all, let's go through the contents. In the first place, I'm going to introduce the topic of queuing theory. Next, I'll be introducing MM1 model and its formulae. And after that, I'll be introducing MG1 model and its formulae, which are also known as Polak-Khinchin formulae. And after that, I'll explain their applications in industrial logistics. And after that, I'll go through example problems related to them. And after that, we'll go through a comparison between MM1 and MG1 models. And after that, we'll discuss about their advantages and limitations. And after that, I'll conclude the topic and give the references for the topic. So first of all, what is queuing theory? A queuing theory is a theory that studies waiting lines or waiting queues. For example, a queue of customers are waiting at a place. The theory which studies that queue is also known as queuing theory. It's used to model systems where customers wait for service. For example, trucks, packets, jobs, or even people. In industrial logistics, queuing theory helps to predict delivery times, loading delays, and resource efficiency. The key elements of queuing theory are arrival rate, which is denoted by lambda, service rate, which is denoted by mu, number of servers, and queue discipline. So let's go through MM1 model. What is MM1 model? It's a simplest queuing system model. Here MM1 stands for Markovian, Poisson arrivals at the first place, and Markovian, exponential service times at the second place, and one server. MM1 model is used when the arrivals and service follow exponential distributions, and it is also used in common in single server systems. Best example is one loading dock. So this is the explanation for MM1 model. Now let's discuss about MM1Q formulae. Arrival rate lambda. It is an average number of arrivals per time unit. Service rate mu. It is an average number of services completed per time unit. Utilization factor. Utilization factor is denoted by rho, and its formula is rho is equal to lambda by mu. It should be lesser than 1 for stability. Average number in system. It is denoted by capital L. Its formula is capital L is equal to lambda by mu minus lambda. Average number in Q. It is denoted by LQ. Its formula is LQ is equal to lambda square by mu into the whole of mu minus lambda. Average waiting time in system W. It is denoted by W, which is equal to 1 by mu minus lambda. And finally, average waiting time in queue. It's denoted by WQ. Its formula is WQ is equal to lambda by mu into the whole of mu minus 1. Hence, these are the formula for an MM1 queue. Now let's go through MG1 model. In MG1, M stands for poisson arrivals, G stands for general service time distribution if there are any, and 1 stands for 1 server. Just like in MM1 model, it is used when service times are not exponential, and it is applicable in logistics systems where processing times vary. Best example for this is different truck loading durations. Now let's discuss about MG1 queue formulae, which are also known as Pollaczek-Khinchin formulae. Mean service time is denoted by E of S. Variance of service time is denoted by var of S. Here, as we know, S stands for service time. Utilization factor, denoted by rho, is equal to lambda into E of S. Average number in queues, LQ, is equal to lambda square into var of S plus rho square by 2 into 1 minus rho. Average waiting time in queue, WQ, is equal to LQ by lambda. Average waiting time in system, W is equal to WQ plus E of S. Hence, these are the formulae for MG1 queue. Now let's go through applications of these queues in industrial logistics. These queues are used to predict truck waiting times at loading docks. These queues help optimize resource allocation. Best example we can take is scheduling forklifts or cranes. It identifies bottlenecks in warehouse operations, and it helps reduce operational costs by minimum idle time and congestion. An example we can take is the estimation of average waiting delay when trucks arrive randomly and loading times vary. Hence, these are the applications. Now let's go through an example problem. For MM1 queue, let's consider that given lambda is equal to 3 trucks per hour, given mu is equal to 5 trucks per hour. The given question is to find average waiting time in queue, that is WQ. WQ, just like we discussed before, its formula is lambda by mu of mu minus lambda, that is 3 by 5 of 5 minus 3, that is 3 by 10, that is 0.3 hours or 18 minutes. Hence, this is an example problem for MM1. Now let's go through an example problem for MG1 queue. Given problem, lambda is equal to 4 trucks per hour, E of S is equal to 0.2 hours, var of S is equal to 0.01 hours square. We know that rho is equal to lambda into E of S, that is equal to 0.2 into 4, that is equal to 0.8. Given problem is to find LQ, that is equal to lambda square into var of S plus rho square by 2 of 1 minus rho, that is equal to 16 into 0.01 plus 0.64 by 2 of 0.2, that is equal to 0.8 by 0.4, that is equal to 2 trucks. WQ is equal to LQ by lambda, that is equal to 2 by 4, that is equal to 0.5 hours or 30 minutes. Hence, this is an example problem for MG1 queue. Now let's compare MM1 and MG1 queues. The arrival processes of both are same, that is Poisson rate, lambda. The service time for MM1 is exponential, that is rate is mu. But for MG1 it is general distribution. Mean is E of S, variance is var of S. Server count is 1 for both. Traffic intensity or utilization is rho is equal to lambda by mu for MM1. Rho is equal to lambda into E of S for MG1. Key performance formulae for MM1, it is closed form, simple. For MG1, it is Pollaczek-Khinchin pk formula, and it needs E of S square. Average waiting time in queue, that is WQ. For MM1, it is WQ is equal to rho square by lambda into 1 minus rho, or we can say LQ is equal to rho square by 1 minus rho, whereas for MG1 it is WQ is equal to lambda into E of S square by 2 into 1 minus rho. Sensitivity to service variability. For MM1 it is fixed, that is coefficient of variation CS square is equal to 1, but for MG1 it explicitly depends on variability. Flexibility or realism. For MM1 it is simple or analytically neat. For an MG1 it is more realistic for variable service times. Typical industrial use. For MM1, small or simple loading or unloading with memoryless service. For MG1, it is variable loading systems, batch jobs, service times with better known variance. We have to choose MM1 when service process is close to exponential or as first cut model. We have to choose MG1 when service time distribution is non-exponential or we have variance data. Hence, this is a comparison between MM1 and MG1 queues. Now let's go through advantages and limitations of usage of these queues. Advantages. It predicts queue delays accurately. It helps plan resource allocation. It simplifies logic or logistics modeling. Limitations. It assumes ideal or random arrivals. It doesn't consider priority queues. It may not be able to handle multiple servers well. So that we need MMC models for this. Hence, these are the advantages and limitations of the usage of these queues. Now let's finally conclude the topic. Hence, queuing theory provides a strong mathematical basis for predicting delays. MM1 and MG1 models are foundational tools in industrial logistics. They help reduce costs and waiting time. Real-world logistics often need simulations or advanced models like MGC or network queues. Now let me give you the references for this topic I have took. I have referred to the book Fundamentals of Queuing Theory, which was written in 2008 by Gross D. Shortle, J. F. Thompson, J. M. and Harris C. M. I have referred to the book Introduction to Operations Research by Hitler F. S. and Lieberman G. J. in 2015, and a lot of industrial case studies from logistics optimization systems. And finally, I would like to sincerely thank the respected professors who had given me this wonderful opportunity to speak on this wonderful topic. Thank you.